let's go ahead and get started.
Probably been up on your desk for quite a while.
I don't keep it here. I usually keep it in the cabinet. Anyway, so today we are going to continue on in chapter 5. All right. So we started talking about light and the quantum nature of the light, how light is both a wave and a particle, okay? And the whole reason why we talked about light, and we mentioned this right at the end of class last time, the whole reason why we need to talk about light before we can talk about electrons is because, as it turns out, electrons kind of behave the same way. Sometimes electrons are a wave, sometimes they're a particle. It just kind of depends on how we're measuring them. Okay? So as chemists are building and refining their model of the atom, okay? If you're looking for the page we're on to follow along, it's page 146. So as we're refining the model of the atom, we are just trying to figure out really what's going on. What is happening here? So there's a scientist by the name of Niels Bohr. Niels Bohr, B-O-H-R. So he takes this idea of quantum and applies it to the atom. Right? Because as you remember, we had no idea why the negative electron was not smashing down into the positive nucleus. We couldn't figure it out. There was no reason for it to not do that. So he came up with this idea that just like light, electrons had to have a specific amount of energy. Now they could have different levels of energy, but there was a very definite smallest energy level that they could have. And that's what kept them from smashing down into the nucleus. Now, we have a special name for the lowest energy that electrons can have. We call it the ground state. Ground state. Right? So that is the lowest energy that an electron can have in the atom. If we put more energy into it, it can jump up to a higher state, but still keeping that idea of quantum, there's only specific allowable energy levels. Okay? Now, Bohr did give each one of these levels a specific number. We call it a quantum number. And he was able to actually figure out a whole bunch about them based off of the absorption spectrum. Remember when we talked about that? Yes, no? Sort of, not really. Let me get the poster again.
Oh, the light one? The absorption? It absorbs some light and reflects others.
Okay. Now, what Bohr was working with is actually hydrogen. So this one right here. Hydrogen is one of the simplest ones, as you can see. We have 4 lines in the visible spectrum. Okay. And he realized something. He said, all of these different light wavelengths, they correspond to a specific frequency, right? And as we learned, frequency can be related to energy. So these energy levels of the different states, whether it's the ground state or a higher state, we can figure out what those energy levels are based off of these frequencies. Okay? So what he figured out is each one of those lines represents an electron jumping between levels. Okay? That's what these actually represent. Electrons jumping between levels. And so he was able to figure out approximate radiuses, or radii, that's the right way to say that, radii for these different levels. Because once you have frequency, you can figure out wavelength. Okay? And so what he said was, for the quantum number 1, the ground state, okay, that radius of the orbit is 0.0529 nanometers. And then for the second one, 0.212 nanometers. And so based off of these frequencies, we can calculate the wavelength, and we're going to assume that the wavelength of light that is able to make this electron jump corresponds to the size of the radius. Okay. Have we completely lost everyone?
Not really.
Okay.
I lost nothing.
All right.
Hang on.
Honestly, that's not a big deal, because this is a lot of quantum concepts that I'm not as concerned that you know these. Okay, so if this only is sort of making sense, you're going to be fine. So just stick with us. Don't get overwhelmed. Okay. Now, essentially, what happens in his model is we get something like this. Okay. Now, hydrogen, and look at our periodic table, it's number 1. So we have 1 proton. Okay? And it sits right there. Okay? Now, since I'm holding this up, I'm going to put the proton down. Just remember it's right there. Okay? And then we have 1 electron. Okay? So the way that it works, this is going to be the ground state. So this electron can be anywhere right here. Okay? That's the lowest energy it can have. But it also could absorb some light and go up to this one. Okay? So it can be here, or it can be here, but it cannot be there. That electron can never be there. It's not allowed to. It has to either be here or here. Okay? And this model works really well to explain all of these. There's a problem, though. It doesn't explain anything but hydrogen. Now, we will still use this model as a basis for some other ideas, but just keep in mind this model only truly works for hydrogen. Okay, so the next time we pull this out, just remember that. We're doing it, we'll use it to solidify some concepts, but it's not technically 100% accurate for anything other than that. So we had to find some other model. Okay? And this is where we really start to get into the quantum mechanical model. Oh, no. This is where we start to treat electrons not only as particles, but as waves. Okay? Just to warn you, don't be afraid. Okay?
You go just to warn you, but don't be afraid.
Just to warn you, this is weird. Okay? This is weird. So we're going to go through it and explain it to you, and then we're going to ignore it.
Okay.
Okay? So don't get overwhelmed. Okay? Everything's going to be okay. So electrons can behave as a wave as well. And how that correlates to quantum, where there are, these finite numbers that can happen, but nothing in between. There's a nice picture on page 149 that sort of explains that. What it says is it has to be able to go around that orbit and come back to exactly the same spot. Okay? You have to be able to have the orbit size be an exact number of wavelengths. You can't have a fraction of wavelengths. It just doesn't work because it has to be what's called a standing wave. And yeah. So we have what's called the de Broglie equation. And here's where things get really weird. Because trust me, this is all very not weird stuff compared to what it could be. The de Broglie equation tells us any moving object also behaves like a wave. So you walking down the hall are a wave. Okay. A car driving down the street, it's a wave. Okay. And there's an equation to calculate your wavelength.
Okay. There's an equation to calculate us as waves.
Yes. And it's right there in your book on page 150. So lambda equals h. Okay.
Oh no.
Oh, that's actually,
No.
that's not a nu. We want just a straight v, that's velocity. Okay. So if a car driving down the street is behaving like a wave, why doesn't it look like a wave? Well, let's look at this. Okay. Let's say that your car, the mass is 1,000 kilograms. Okay. The velocity, just pick a velocity, we'll say it's moving at 10 meters per second. Remember what h is?
0.00.
6.626 times 10 to the minus 34.
That was really wrong.
Okay. So let's put this in. Here it is. So we put in our value for Planck's constant.
We're not in 2 points.
And then we divide by 1,000 times 10. And the wavelength. So how much this particle is behaving like a wave is, well, for this example, 6.626 times 10 minus 38 meters. That is so incredibly small, you can't see it. Okay? So things that have large masses,
Like the ocean.
okay, like the ocean, or even just you, or really anything that is big enough that you can see it, their wavelength is so small that it is negligible. Okay. Does it have a wavelength? Yes, but you can ignore it. But when you get really, really tiny things like an electron, then you can't ignore it anymore. Okay? So here's the thing. Treating electrons like waves is super annoying. It's complicated. I'll leave that for your college chemistry professors.
Oh no.
Okay? For this class, we're really going to treat them as particles. Okay? We're going to treat them as particles. So don't stress about all of this because you'll never see that again. Anyway, I do want to bring up one thing. We have something called the Heisenberg uncertainty principle. And it's honestly, it's pretty straightforward. What it says is we can, as scientists, so we can, as scientists, we can measure where an electron is, and we can also measure how fast it's moving. But you can't know both at the same time. You can either know where it is, or you can know how it's moving. But when you measure one of them, it fundamentally changes the other. What? And so you can't know both. So just keep that in mind.
So what you're saying? Huh?
When you measure the position of an electron, it changes that electron's velocity.
Oh.
When you measure the velocity of an electron, it changes its position. So you can know one, but knowing that one changes the other. So you can't know both at the same time.
That's so paranoid. That's so.
That's so paranoid.
So just.
So, what we end up combining all of this, okay? What ends up happening, and this is what we have for the modern model of the atom. Okay? This is what we actually use. Okay? This is what I had to do in college. Okay? This is the modern model. Okay? We have what are called orbitals.
Oh, there we go.
Okay? And we've done a lot of complicated math to create a three-dimensional shape that has, is it 90 or 95%?
I think it's
90%. There's a 90% probability that the electron is somewhere in that three-dimensional shape. Okay. It's not a guarantee. Remember, there's a 10% chance that it's not. But there's a 90% chance that we will find the electron in this three-dimensional shape. Now, there are a lot of different orbitals. If you look at page 154, you can see the s orbitals, the p orbitals, and the d orbitals. Now, I don't know why, but this book does not include the f orbitals. So I'm going to put the f orbitals up on the screen for you here. Give me just a second.
Those are like the weird ones, right?
They all look weird.
They're a little bit unique, yes. So,
Engine's first four.
Oh, Mr. White, you got a new picture.
well, I have a new kid, so I needed a new picture.
Oh, another one. That's 4.
Yes, there are 4 kids in there now. Okay, where are we?
What random things?
Where is it? No, I have a picture here. Is somewhere. Give me a second. Oh, here we go. All right. There it is. So, what we are seeing here, so this, starting at the bottom, we've got the s orbital, which is a sphere. That's in your book. That one makes sense. The p orbital, you'll often hear those called like dumbbells, because they have the 2 kind of cone-shaped things. And there's one on each axis in 3 dimensions: the x-axis, the y-axis, and the z-axis. Then you get to the d orbitals. Now this actually shows an alternative version of the d orbitals, but most of the time we're just going to use the common ones. Okay.
Wait, which one? Oh, the top one.
That, yeah, the one on top where it says common. And then we get to the f orbitals. The f orbitals are just kind of weird. Okay, like me. So we have all these different shapes and all sorts of weird things going on. And yeah. So like we said, we have a 90% probability that if an electron is in the s orbital, it's in that sphere. It doesn't have to be, but it most likely will be. So that's really all we need that for, because the fact of the matter is, I don't really need you to know what the orbitals look like. Okay? But we are going to move on into section 3, where we can sort of get to how we're going to use this information. Okay? The fact of the matter is, how the electrons are arranged around an atom determines how that atom is going to react. You change the number or the arrangement of electrons in the atom, it is going to behave differently. So what we're most interested in is how the electrons are stacked around the nucleus. Okay? So we call this the electron configuration. And we need to be concerned about mostly the ground state. Okay? Now remember, the ground state is the lowest possible energy levels for all of the electrons in this atom. Okay? And to figure out what the ground state is, we use something called the Aufbau principle. That is a German word. It means to build up. Okay? The Aufbau principle.
Did you have to speak German? Did you have to speak?
I do speak German, yes. Now, the Aufbau principle just says you start at the lowest possible energy and you build on top of that. Okay? Now, there's this lovely chart on page 156 with all these different colored boxes. Okay? And that tells us how we are going to build the electrons. Okay? We're going to start at the very bottom, the 1s orbital. Okay? So 1s means you are in the s orbital, so it's the spherical one. And 1 tells us the quantum number, which means it's the very smallest one. Okay? Now, if you notice, looking at this chart, quantum level 1 only has one orbital in it. Okay? It has one s orbital, and that's it. Okay? Now, each one of these orbitals can hold 2 electrons. Now, if you want to get technical, one of them is going to spin up, the other one is going to spin down. Don't worry about that. We are not dealing with electron spin, but as you look at these diagrams, you will notice that it accounts for the spin. Okay? Electron spin is something way beyond what I'm going to teach you. Just so you know, that's what those arrows in the boxes mean. Okay? Now, what we do, we need to figure out how many electrons an atom has, and then build a chart. Okay? That's what we're going to do. So we're going to do a little bit of practice here. So let's pick an element. Let's pick boron. Okay? So how many electrons will a neutral boron atom have? 5. 5. Why is it 5?
It's got 5 electrons.
Because you look at the periodic table and the atomic number is 5, which means it has 5 protons, so to be neutral, it has to have 5 electrons as well. So right now, whatever the atomic number is, that's how many electrons it's going to have. Okay? That won't always be the case, but we'll get to that later. So we have 5 electrons. So we draw this chart, sort of what it looks like. So we've got this box, it's labeled 1s. Now above that, you have the 2s. And then off to the side of that, we have 3 boxes, which are labeled 2p. Now that should make sense. Because remember when we looked at the orbitals, there was one shape for s. Okay? But when we got to the p orbital, there were 3 different shapes. Okay? That's what those 3 boxes represent on this diagram. Those 3 different orbitals. Okay? Now that's going to be enough boxes for us for 5 electrons, so we won't continue to draw it. And this is what we do. We start at the lowest level. And we put an electron in with spin up. And then we put another one with spin down. Okay? So now we've filled this lowest level, and we've used up 2 of our electrons. So if we've used up 2 electrons, how many are left? We started with 5, we used up 2. So now we have 3 more that we need to put in. Okay. So we go to the next lowest energy level. Okay. Put spin up, spin down. So now we've finished this level because we can only put 2 in each box. So now we've used 2, 4. How many are left? Started with 5, we used up 4.
1.
There's 1 left. There we go. This is the electron configuration for boron. Okay. Now, how do we write that? Because we don't want to have to draw this every single time. What ends up, we actually end up doing, so we write the orbital, so 1s, and then like an exponent, we put how many are in that orbital, which is 2. So we have 1s, 2, and then we go to the next energy level, 2s2, and then 2p1. This is truly what we would consider the electron configuration for boron. Okay. Now I will mention, if you are filling out boxes like this, let's say, well, let's go to the next one, carbon. So carbon has 1 more electron. Now it's going to be in the 2p level. And really we have 2 options. We can either put it in a new box or we can fill up that box. Okay? Any guesses as to which we do?
No, the bottom.
So you're saying put it in a new box.
No, keep going.
So put in this one or put it in this one?
And then no, that one.
The second one?
The first
Who says the second one? Who says put it in the first one with this one? Who has absolutely no idea? That's okay, we haven't taught you. It's just, as it turns out, you put it in the second one. Okay? So you put it in this one. You had another one, so this would be carbon. Moving to the next one would be nitrogen, so we have 1 more electron.
And then you start over the next
And
one, right?
then when we get to oxygen,
Then you go 8, then you put boom, right?
you put another one there.
Yay.
Okay. So let's write the electron configuration for oxygen. Okay. So once again, we have 1s, and there's 2 in there. Next energy level is 2s, and there's another 2. 2p, we have 1, 2, 3, 4. That's the electron configuration for oxygen. Okay. Now, if you look at page 158, you can see the electron configuration for the first 10 elements, hydrogen through neon. Okay. And when we get to neon, it becomes, well, it becomes a little bit interesting because you can get these really, really long electron configurations. I mean, for example, element 118. You could do an electron configuration for element 118. It would require a fair amount of time putting all 118 electrons in all these different boxes. So for the bigger elements, really starting with element number 11, sodium, and then anything bigger than that, we can actually use what's called a noble gas configuration. Now, we haven't really gotten into it, but all the way over here on this side, okay, called group 18, it is the noble gases. Now these, for reasons which we will get into, don't react really well. But we'll talk about that later and why. Anytime we get to the end of this chart, we can use that to shorthand our next elements. So if we say neon, so we know that neon actually is 1s2, 2s2, 2p6. Okay? Now, I know that. I can do it really fast, so don't worry if you didn't follow why it is that. But we know that that is neon. And as we continue to build, we know that that's going to be the lowest level of everything beyond that. So what we can do is say those are the same. Put it in brackets, and then we can continue. So sodium we can write like that. Okay? If you were to write sodium completely out, it would be 1s2, 2s2, 2p6, 3s1. But at the same time, we can just say, well, that's neon. So it's neon 3s1. Okay. And I know that this is kind of complicated right now. We're going to practice. Okay. We're going to do some together so that it's not overly complicated. Now, I'm going to show you a trick here. And this is how do you remember what order the electrons fill in. So what we do, we write 1s, 2s, 3s, 4s, 5s, 6s, and 7s. Okay? Because there are 7 s orbitals that we can fill. Now, is there a 1p orbital? No. It starts at 2. We have 2p, 3p, 4p, 5p, and 6p, 7p. Okay. The next orbital is d. Now, there's not a 1d or 2d. It starts at 3. So 3d, 4d, 5d, 6d. You could write 7, but it doesn't fill. We don't have any elements that would get as far as 7. So we just leave it off. And then comes F. Once again, it stops, or it starts one more level lower, 4F, and 5F. So we write this. Okay? And what we do is we just follow diagonal lines. Okay? And what I mean by that, so let's pick a nice big element. pick scandium, which is 21. So we need to account for 21 electrons. Okay. So 1s is always first. How many electrons fit in the 1s orbital? How many electrons fit in any s orbital?
One.
Not one.
No.
It's two. Okay. So the s orbital always has two, no matter what number it is. It has two. We can put 2 there. So now we're down to 19. Then we're going to make another diagonal. The next thing that our line hits is 2s. So that's our next one. Once again, how many electrons can we put in an s orbital? 2. We put another 2 there. We've used up 2 more. We're down to 17. Do another diagonal line. This time we hit the 2p orbital. How many electrons can we put in the p orbitals? We put 6 because there's actually 3 orbitals there. We put 6 there. So 2p6. So now we've used up another 6. We're down to 11. And as we continue to go, we get 3s. How many can we put in the s? 2. We're down to 9. Do another one here. Get to the 3p. 6. Okay. 3. 4s. We're running out of room. 2. Down to 1 electron. Get to 3p1. So that's the electron configuration for scandium.
That's 22.
21.
21. Oh, God.
Now we could shorten this. Okay? So if we look at scandium, which is right here, number 21, we go up a level and all the way over, we get argon. So we can actually use argon, which stops right there. We have that.
That's so much. Like, sure. I'm not even going to do that for 118. Like the regular.
Well, for 118, you just start with radon. It's still a fair amount of writing, but yeah. Okay, so the question is, we figured out 2 and 6, how many will fit in the d orbital? Well, to figure that out, we can go back to our chart on 156. Okay, how many boxes are in the d orbitals on that chart? How many boxes? So page 156.
5.
5. So we have 5 boxes. If we can fit 2 electrons in each of the boxes, how many electrons can we fit in the d orbitals? You're overthinking it. 10.
10.
5 boxes times 2 electrons in each box.
10.
10. Okay. Now, I don't think you'll ever get anything that gets to the f orbital, because those are pretty big, and I'm not going to be that mean to make you do one. But if we look at this, there are 7 boxes, 14, so we can fit 14 electrons in each f orbital, because there's 7 total orbitals. Okay. There's one last thing that we need to cover. And this is actually a concept that's going to come back over and over and over. So if you don't get it today, you'll eventually get it. Okay. And what it is, concept of valence electrons. A valence electron is one of the outermost electrons. Okay. And a very quick way to determine what is a valence electron.
Oh,
Pretty much anything beyond the noble gas configuration. Okay. So we're going to get into that a whole lot more. But that actually, there's one more thing, electron dot structures. With an electron dot structure, we put dots around the element symbol.
Oh, those are kind of easy-ish until you get quite a bit away.
They're not too bad. And each one of those dots represents a valence electron. So if we look at, well, there's a chart on 161. So lithium. Now, if we write the electron configuration for lithium, okay, we can say that we have helium and then 2s1. So we have one electron past the noble gas. So we put one dot by lithium. If, however, we went to beryllium. Now, beryllium is 2s2. Okay. So we put one there and one there because we have two valence electrons. If we move to boron, well, the pattern continues. We now have three. We have 1, 2, 3. Carbon,
4.
nitrogen,
1, 2, 1, 1, 1. Fluorine.
oxygen,
Oxygen, that's fluorine.
fluorine,
And then
neon. So now lithium has more than one electron, but it only has one valence electron, and that's the one that we care about because that's the one that's going to react. So, okay. So that's where we're going to stop. I do have a quick homework assignment for you. So I'll put it up on the board. You can use the rest of the time to work on that. And just remember, we don't have school Friday or Monday.
so are we going to review all this on Wednesday too?
On Wednesday, we'll probably have a quick review, yes, because it will have been a week. And I know that we went over a lot of stuff. So Wednesday, we'll probably hit the important parts before moving on. Okay, so let me put your homework assignment up. It's also going to be on LMS.